Today we are beginning to discuss matrix algebra, but before, I really want to pick up almost where we left off in the last video. So what happened in the last video? We had, if you look at these three black matrices, we had three different linear systems that when we formed the augmented matrix and performed elementary row operations, we got these three different reduced row echelon forms. Okay, this first one had a unique solution. It was XYZ is minus 9, 5, 0. And the third one had a unique solution. It was XYZ is 4, 5, 1. Okay, but the second one here, you see this was XYZ, W is a free variable here. We had infinitely many solutions. And the leading ones are in the X, Y, and Z columns. It made W free, right? Okay, well, then what happened? Then I changed the example. Oh, didn't mean to erase. I changed the example that came from this linear system by just one number, and we stopped here. And you know the blue is not in reduced row echelon form. It is in row echelon form though. And this one had no solutions. And I mentioned at the end, in fact, this definition is just writing down what I said at the end, but this last line basically says 0 equals 1, which is not true. So now let's move to our definition. A linear system is what's called consistent. That's here. If it has at least one solution, okay? Consistent, consistent, consistent. And it's inconsistent if it has no solutions. And this would be like this example. Well, there's a theorem that I would like to mention, although given all the examples we've done, it really shouldn't surprise you, but it's definitely worth writing. So the theorem, there's two parts to this theorem, and the first part is about inconsistent systems. A linear system is inconsistent if and only if let's see, a row echelon form, this is one way to say it, echelon form for its augmented matrix has, well, a row that looks like this, has a row that looks like this. 0, 0, 0, 0, and then there's these dots, and then some C where C is not equal to 0. There's other ways you could state this. You could phrase this statement in terms of the reduced row echelon form for the augmented matrix, but this is fine because in particular, the moment you get zeros and then something non-zero over here, you know you can stop as we did here. You don't have to go all the way to reduced row echelon form to realize that your system is inconsistent. This would say, in terms of an equation, that 0 is equal to something non-zero. And of course, that's not true. Okay, well now the second part of this, and this too should be, at least I think it should be no surprise based on the examples we've done, is as follows. If a system, oh, maybe I should come over here. It's easier to write this way. If a system is consistent, and I mean linear system here, then it either has only one solution or infinitely many solutions. My black is dying. I will switch back to the blue, or infinitely many solutions. Okay, that was perfect on the space. So what the second part says, it starts in black, my black died and ends in, or started to die and ends in blue. The second part of the theorem, it says that you'll never see, for example, exactly two solutions of a linear system. You're going to have one, or you're going to have infinitely many. Well, or you can have zero. But for a consistent, meaning you have at least one, you have one, or you have infinitely many. And these are the only options. Well, what I'd like to define is something called the rank of a matrix. This is for a matrix. It's not for a linear system, because every linear system, we know it has really two matrices. There's the coefficient matrix, and then there's the augmented matrix. So this notion of a rank is of a matrix, okay? So the rank of a matrix A, and this is its notation, rank A, okay? It is the number of leading ones in, well, this is just the reduced row echelon form of A. So that's what this symbol is. Maybe I'll put that in a bracket. This is the reduced row echelon. Something's misspelled. I think it's echelon form of A. Okay, that's what this is. So this is the rank. Now, all three of these, well, what are we looking at? In black, these were the matrices from the last video that were the coefficient matrices of the linear systems we looked at. Not the augmented, right? That would have had one more column, one more column, one more column. They are the coefficient matrices. And then below in blue, I show the reduced row echelon form, which we worked to find, right? All three of these matrices up here, I'll say all three have rank, well, it's really all six if you want to think about it, because these are already in reduced row echelon form. So I will just say all have rank 3. Every single matrix on the board has rank 3. But I was really trying to say something about these three. These are the ones that came from, or they are the coefficients matrices for the linear systems we looked at. So the reason that this has rank 3 is because this is its reduced row echelon form. And you see there are 3 leading ones. Similarly, this has rank 3 because, well, here's the reduced row echelon form. 1, 2, 3 leading ones. Finally, similarly with this one, we have 1, 2, 3 leading ones in its reduced row echelon form. And these all have different sizes. Right over here, these are 3 by 3. 3 by 3, 3 rows, 3 columns. Here we have 3 rows, 4 columns. We have 4 rows, 3 columns. Okay, but they all have the same rank. It's just the number of leading ones in the corresponding reduced row echelon form. Now, let's make a few more observations. Suppose we have a linear system with that has a n by m coefficient matrix. So this is not the augmented matrix, coefficient matrix. That has an n by m coefficient matrix A. So coefficient matrix capital A. Well, let's think about this for a moment. This means A has the following form. It's A11, A12. And then this says we have n rows, m columns. So this is going to be A1m, and then A21, A22, out to A2m. And then we have n rows out to A, N, M. Okay, this is our coefficient matrix. Well, let's make some observations. And this is an important thing to think about with the concept of rank and this concept of the three possibilities that can happen. We either have 0 solutions, infinitely many solutions, or just one solution. Well, first of all, these are the coefficients, right? And what do we know about, well, rank? If we reduce this to row echelon form, reduce it to reduced row echelon form, we will see the leading ones. And we know that you can only have at most one leading one in a row, at most one in a column. So immediately you see that the rank of this matrix must be less than or equal to m, the number of columns, and the rank of this matrix must be less than or equal to n. This is an and, okay? Well, we can say more. In fact, let's go back to the linear system. If this is the coefficients matrix, so every row of the coefficient matrix corresponds to an equation. We have n rows, so you see we have n equations in our linear system, and every column of the matrix corresponds to a variable. Remember, we just saw this, for instance, even in this video, I was talking about x, y, z, w, and pointing to the columns. Okay, so we have m unknowns or variables. Okay, so now let's think about what can we say? So this number m is the number of variables. This says a lot. So m, total number of variables. Well, it's going to be the rank, this is the number of ones, leading ones, excuse me, maybe I'll write that underneath. This is the number of leading ones in the reduced row echelon form of the matrix. And then plus, well, any column that does not have a leading one, this one is a free variable, right? So plus the number of free variables. We saw one example where we had one free variable. It was, let's see, x, y, z, w. It was here. But the number of columns, this would be the number of leading ones plus number of free variables. These are the columns that do not have a leading one. So now let me break into some cases. We can think about some things that can happen. Okay, so if your linear system has a unique solution, well, then we know something about the rank. I'm just going to try to get a new blue. Okay, if it has a unique solution, well, let's just look at this equation above. It says you have no free variables. So this says m, the rank of A is m. Then the rank of A equals m. And here this is, I'll write it underneath, this is number of columns. Okay? Parentheses. Now what else can we say? There's more things we can say, even looking here. So if a system has infinitely many solutions, well, I'm looking at the exact same equation. Infinitely many solutions happens precisely when you have at least one free variable. I mean, maybe you have more than one, but you have at least one, okay? So this says the rank of A is strictly less than m. Then, I'm going to have to write it on the next line. The rank of A is strictly less than the number of columns. Okay, now there was one more thing that happened. We have a unique solution, infinitely many, or no solutions, which was our inconsistent system. And what can we say about the rank in this case? If a system has no solutions. Well, this, remember, is coefficient matrix. If we did the augmented, so augmented, we have one more column here. So now imagine we're looking at this, but instead of this line, I'm going to leave it. I'm just imagining things. Okay, I have dots, and then I have some numbers here, right? This would be augmented. We have one more column. What it means is that you have a whole bunch of zeros followed by something non-zero here, right? That's the only time we can have no solutions, as I just mentioned. Well, that would say you have at least one. Now I'm going to ignore this, but if you have no solutions, then in the reduced row echelon form of the coefficient matrix, erase this because I'm talking about the coefficient matrix. In the reduced row echelon form for this, you have a row of all zeros, at least one. Maybe you have 2, 3, 4 rows of all zeros, but you have at least one so that you can get the all zeros. And then when you add this extra column, you have a non-zero thing. Okay, so if you have no solutions, well, the rank must be strictly less than the number of rows, which is here, because you have this row of all zeros. Then the rank of A is strictly less than the number of rows. So this is, our first glimpse into just looking at the matrix A and its rank. We have some things we can say. Well, I guess the way it's written, and those of you who have had, for instance, math reasoning, you would be able to say some things. This is if-then. All of these are if-thens, and I start if a system, then I say something about the rank. But we also know that implication is equivalent to contrapositive, and that would start off with the if something about the rank, and then I would be able to say something about the system. And these are some nice observations to make. Now, I want to make one more comment, and that is when you have a square matrix. Okay, so one more comment is when this coefficient matrix is square, and just say it's n by n for the moment, or I could have done m by m, but it's fine, n by n. So then, well, if the linear system has a unique solution, well, or maybe I should not do an if-then here. I will just make it a two-way implication, and I will say the linear system has a unique solution if and only if the rank of the matrix, coefficient matrix A, is, well, here it's n by n, so the rank will be, you will have a leading one in every single row, equivalently in every single column, because you'll have, the rank is full, so the rank would be n. And then this would be if and only if you have an n by n square matrix that has, well, n leading ones, what can its reduced row echelon form possibly look like? We have one choice. So if and only if the reduced row echelon form of A is this identity matrix. And this is what I was saying when we were solving, and I even said, oh, we're going to see a little 3 by 3 identity over here on this side, which was the coefficient matrix. This is what we get when you have, say, the same number of equations as you have unknowns, or the same number of equations as you have variables. If you are in the case where you have exactly one solution, your reduced row echelon form, it's the identity matrix. And you can very quickly read the solution off. let's say A is this matrix A, I, J, and B, maybe, okay, I was just going to put a comma. It's fine. B, I, J. Suppose these are both N by M matrices. And we have C is a scalar. Scalar, okay, means number, right? It's not a matrix. I mean, technically, it's like a 1 by 1 matrix, but we're just thinking of it as a number. Okay. Well, okay, it's quite simple to add two matrices and to multiply by a scalar. If you want the matrix A plus B, it is entry by entry. So the ij entry is just A ij plus B ij, okay? You take the row I, column A, entry in A, add it to the row I, column J, entry in B. Well, there you go. And similarly, C, let's say A. So take a constant times the matrix. And all you do is you multiply every single entry by the constant. Okay, so let's do two quick examples maybe, and then we will move on to some other things. If we had 3, 2, minus 1, gotta line it up, minus 1, 7, 8, minus 3. We add it to the matrix. Well, it has to be the same size or you can't make the sum. They must be both the same. So this is 3 rows, 2 columns. This must be the same size. Okay. So maybe this is 1, 0, minus 1, 2. Oh, okay. And then 0, 6. Fine. We add component by component or entry by entry. So the 1, 1 entry is 4. And then we have 2, minus 2, 9, 8, and 3. Okay? And similarly, if I wanted, let's say, I draw a line. If I wanted, say, 5 times this matrix, 1, 0, minus, I'll just use one of the ones we just did. We just multiply every single entry by 5. So this would be 5, 0, minus 5, 10, 0, and 30. Okay, this is matrix addition, scalar multiplication. As a special case of the matrix addition, where it's entry by entry and scalar product, we get what you know or you have likely seen for vectors. So we get vector addition and also scalar multiplication, because a vector this is just, well, it's a, let's say, n by 1 matrix, right? A vector, we think of column vectors, as I mentioned last time. So if we have, let's say, V is 5, 2, 7, 1, and W, this is going to have to be in our 4, 0, minus 1, minus 3, and 2. And then I need to, let's say, well, I'll do a scalar in a moment. Then we add, and I even mentioned this briefly in the last video. I'll let it write it down. I had 2 vectors in R2, and I just said, well, if you added them, you would add component-wise. And this is what we do for vectors. So we add, we get 5. We have 1, 4, and 3. And this thing that I drew in the plane about thinking about arrows, that really is the geometric picture. So I will write it now. It's called, this is the parallelogram rule for adding vectors. And there's also a triangle rule. But honestly, they do the same thing. The only thing is that this one, it's not going to work if you tried to say add a vector to itself, and I'll show you that in a moment. So if you have 2 vectors in the plane, you connect their tails here. So if this is V, we connect the tail of W to the tail of V, and as I mentioned in my last video, I did it in R2, but this is very general. If you have two vectors, okay, these really could have, this is my V and my W. Maybe I will put the right color to it. Here's V, here's W, okay. These could have 15 components and really be in R15, and I could still do this, right? It's fine. In any case, so in the parallelogram rule, as I mentioned, these form sides of a parallelogram, and what the parallelogram would have to be, well, this would be a third side, and this would be a fourth side, and then you put the tail here, which is your little origin, and then it goes out to this corner of the parallelogram. This is V plus W. The issue, though, is if you want to add V and V together, for example, this won't work. Or add V and any multiple of V, which I haven't even drawn or talked about scalar multiple yet. But we will see, it won't work, because if you try to add V with V, it won't form two sides of a parallelogram, okay? So in times like this is why we love the triangle rule. Triangle rule, well, what is it here? What you do is, maybe I'll just write it, is you connect, and then I'll draw a picture. You connect the tail of W to the head of V, and then I'll put like this, as in the picture. So now let me try to see if I can draw the exact same two vectors. Okay. So V was something like this, V. And then W, well, I see it here, okay? But I want to connect the tail of W to the head of V, would be maybe something like this. Here's W. And then connect, okay? And this way will work. This is the triangle rule. This way works even if you wanted to add V to itself. Okay, so this is the vector sum. Now I erased my example, but if we wanted to multiply, if we have V is, and I'll go back to R4, say 5, 2, minus 1, 0, and I wanted a constant times V, so now I have a scalar, it's a number. If I want this, well, let's, for example, do 3V. This is just like, well, it's just a scalar multiplication of a matrix, or it's the same type of operation where this is a 4x1 matrix. So we would just multiply component-wise. This is 15, 6, minus 3, and 0. And the picture, I have space. Okay, if I have V, this arrow, here's 2V, which is V plus V, okay? And then here's 3V, right? And I'm doing this triangle rule. This is, as I mentioned, parallelogram rule won't work, because if you just line them up, you don't get a parallelogram. It falls on top of itself. So if you put them, here's the tail head, connect the tail head, connect the tail head like this. This here is 3V, or generally, this would work for any, let's say, non-negative integer multiple of V, but you just stretch it out by a factor of whatever you're multiplying it by, except this, which is an important observation, is technically minus 1 times V. Now, algebraically, you just multiply every single component. The arrow, it changes to the other direction, so it would be like this, minus V, okay? If this is V, you just flip the arrow around like that, minus V. It's the opposite direction of V. Now there are products too. We will get to multiplying two matrices later, but what I'm going to talk about two products today, okay? And both are very important. Number one, this is the dot product. And this is when you multiply, or it's one form of multiplying, I'll put in quotes, but what this product takes in is for two vectors. And then I will talk about the product, let's say AX, and this is a matrix times a vector. And really, before we can get into the second one, we need to understand dot product anyways. Now, what is dot product? Well, this came up in our last homework a little bit. It was defined, you had to use it, but we will go through it again or more now. For the dot product, this means it's a product, one of the products, but is the one we are talking about today for two vectors, okay? V, W, we need them both to be the same number of components, so they're both n by 1, or you could think of them as 1 by n. This product it doesn't really differentiate between rows or columns. In fact, I'll give you a second way to think about it after we do an example. But we just need two vectors living in the same Rn. And then, well, I need some components here. So I'll write them as columns, but they don't necessarily need to be. Suppose this is V and this is W. Okay, the dot product, V dot W. The most important thing to remember, it's a number, okay? Dot product gives you a number. And the number is, well, you just multiply the first two entries, add, then you multiply the second two entries, add, multiply all the way out to the last, oops, this should be a V. Vn, Wn. Or you could write this in summation notation if you wanted to, Vi, Wi, okay? This is the dot product, and it is without a doubt a scalar, right? Okay, let's do a quick example. You did have this in your homework for the last section. So let's take 2 minus 3, 5, dot, minus 1, 1, 1. Now what are we going to get? Well, we take 2 times minus 1 plus, it's a minus 3 times 1, and then plus 5 times 1. And you notice here, well, this is minus 5 plus 5, we get 0. And as you saw in the homework, that was for the last section, what this means, if the dot product of two vectors is 0, it's called perpendicular. Maybe I'll just write that here. So these are perpendicular because, well, if one is V and one is W, I didn't label them, but because their dot product is 0. Okay, for example, this is the dot product. And let me show you another way you can think about it. I mentioned that the dot product really doesn't care if you're a row vector or column vector, okay? You just have to have two vectors that are the same length. So we can think about dot product where, let's do these exact two ones. I line up my first vector as a row. I line up my second vector as a column. I'll put the dot. It's fine. I'm doing dot product. Okay? And then, let's see. I've got to do this so that I go the same way that you would. You kind of go like this. I'll do it one more time. Get ready. You go over and down like this. Okay? We're going to do that so many times this semester, you don't even know yet. Go like this. One more time. Over and down. Here we go. What I mean by that is you take and you multiply these two. Then you go here. Multiply these two. Then go here. Multiply these two. And in fact, you see it's exactly the dot product. Okay? This is just a way to think about it. And why am I doing this? Well, it's going to come to you. That was my reenaction of the motion that you make when you think about dot product as a row, sort of times a column. Okay. You know, it's funny, if I'm in a class, sometimes I get really amused by something, as I just did, and I look out, and sometimes people are amused, and sometimes people are not. Here, and I have no idea if you're amused or not. Well, this is the joy of doing this at home. I'm just going to pretend everybody's amused. Okay, now, what do I want to talk about next? Okay, well, what I would like to think about is a times x, because dot product we will do more of. So now let's consider this type of product. And this is a matrix, and this is a vector. And in fact, there's two ways we're going to think about this. We will think about this two ways. And we will think about both ways today. We're going to have a row version of what is a times x. We'll have a column version in terms of what is a times x. So first, let's start with the one that's more related to dot product, which is the row version. So let's suppose we've got, now, it's not always defined, just like the dot product of two vectors is not always defined. They have to both be the same length. And in this case, we need there's some restrictions, I should say, on when you can multiply a matrix by a vector. So let's think about that first. A is going to be n by m. N rows, m columns. In order for this product to be defined, we need this to be a m by 1. And the way I always think about this is here in the middle, this middle will match. And then you can form the product. If the middles don't match like this, you can't multiply. And I'll show you in a second. Okay, now, what's the row picture or this first way of thinking about a times x? Well, suppose, how many rows do we have? We have n of them. So let's suppose the rows of A are, I need n of them. W1, W2, Wn. So then, okay, AX equals, well, let's write it like this. This is W1, W2, out 2, Wn. N rows, M columns, very nice. Now this is a whole row, so I will denote it like this. It's a whole row. It's a whole row. It's a whole row. And then I have this vector, which is m by 1. Okay. Well, when you take a matrix times a vector, you can see it here. This will be, I'm going to remove my rows to talk about it. Let's just change this to the rows. This will be, you make the product, it's AX, and the size of this will be n by 1. Okay, well, I need to tell you the n different entries, and here is the way they are. This will be, So this times this is going to be W1.x. That's a number. W2.x. That's a number all the way out to Wn.x. And that's a number. Now, first of all, why can we even make these products? Well, you see, we have m columns, which means each of those, the rows here, and these are in are m, because that's how many columns we have. So each row is in R m, okay? And look, x is a vector in R m. So this product here, the dot product, is defined. So we take W1.x, that's a number. W2.x, that's a number. All the way down, Wn.x, that's a number. Now we have an n by 1 vector. And this is what a times x is. Now let's do a couple of, I'm going to do 2 examples. You see we have 3 rows by 4 columns. This vector is 4 by 1. Okay, very nice. The result will be a 3 by 1. Okay, vector of length 3. Here we have 1, 2, 3, 4, 5 rows. We have 2 columns. This is a 2 by 1. Okay, very nice. We will have a 5 by 1 vector of length 5. And well, we take, this is the row picture I was talking about. So we take this row and dot it with this vector, be 5 times 0 plus minus 1. Okay, maybe I'll write an intermediate step. It's our first one. But we do exactly this operation that I was showing you. Okay, so 5 times 0 is 0. Minus 1 times 2 is minus 2. Then 2 times minus 1, minus 2. 6 times 3 is 18. Okay, then we move down. So this dot product is the first entry of this vector. Okay, then we move down. 0 times 4 is 0. 3 times 2 is 6. This is 0, and then 3. Here, 0 times 2. 2 times minus 1, and then minus 1 times 3. And then all I need to do now is just add some numbers. We get 14, 9, minus 5. Okay, and you see, in fact, we do have a 3 by 1. Okay, well, what about this one? This one's going to be a very 5 by 1. It's going to be a tall. Okay, so this is 10 plus 2, 12. Then the next entry, 6 minus 1, 5, right? And then we have 2 minus 4 minus 2. We have minus 2, and 0 is minus 2. And finally, 2 and minus 6. Okay? So this is matrix times a vector, where you take the rows of the matrix, dot it with a vector, it gives you the entries. Okay? But, for example, or for non-example, I should say, if I tried to, well, okay, I'll show you here. We got a 3 by 1. Here, we got a 5 by 1. If I tried to multiply this vector, minus 1, 3, 0, 2, 0, 2, 6, 1, minus 1. If I tried to multiply it by, say, just this, 0, 2, minus 1. First of all, if we tried to check, this is 3 rows, 4 columns. This is 3 by 1. This is a problem. I'll do it in red. You see, these don't match. So this is not defined. This product, but you'll know it's not defined. I mean, even if you try to check, because if you try to take this row and dot it with this vector, look what happens. Okay, 5 times 0, then 0. Minus 2, but then there's no entry to multiply by this 6. So this row dotted with this is undefined. This is sort of where you see the trouble. And so we really need this. It says the number of columns of A. Maybe I'll write this. Oh. Sometimes my markers jump out. Okay, so what we need is that the number of columns of A must be equal to the number of entries in X for this AX to be defined. Number of entries are just the length of the vector, okay? And we see 1, 2 examples, we see a non-example. AX way number 2, which is the column. We look at columns. Okay, well again, we will still have A is N by M, and X is, here I'm going to need some components. It's going to be X1, X2, out to XM. This is M by 1, okay? And the middle ones match. We can make A times X. I'm going to get the exact same thing. I'm just using a different viewpoint. So let's suppose that V1, V2, how many columns do I have? M. V3 to VM are the columns of capital A. Okay, so then if I make this AX, this product, now I've got to draw these as columns. So I have V1, I have V2, maybe I'll make this a little longer. I have VM, and they're columns. Okay, and then I multiply this by X, which is X1, X2, XM. Okay, and I mentioned this right over here, right before I erased. The only way that this is defined is if the number of columns is equal to the number of entries. Well, in this viewpoint, we don't take dot products. This is X1 V1 plus X2 V2 plus out to XM VM. So I'm just multiplying. This is a sum, right? I'm adding up all of these vectors, but with these multiplied. And this has a name. It's called linear combination. So maybe let me just give you the definition of a linear combination, although literally we see it here. Then I will do the last two examples that we saw. I'm going to do them in this viewpoint. So definition, B, vector B is a linear combination of vectors X, or excuse me, V1 to VM, provided there exists scalars X1 to XM with B equals X1 V1 plus X2 V2 plus XM VM. This is the definition of linear combination, and you see that's what this is. If you take A times X, it's a linear combination of the columns of A, okay? Now, I'm going to come back to this and do some examples of linear combination very shortly, but I really want to go back to those two examples that we saw where we took A times X, but I want to do them in the column viewpoint. Okay, so it's literally the same examples. However, we're viewing this the other way, which is we take a linear combination of the columns So we take, let's write it out, 0 times the first column plus 2 times the second column plus, it's minus 1, excuse me, minus 1 times the third column, and then plus 3 times the fourth column. Okay, you see how this seems like a different operation per se, but we are doing the exact same thing, which we will get a times x here. So let us add these together. Well, this is one reason we practiced multiplying a scalar times a vector, adding vectors, is for right now. Well, this is just, if I add, this is going to be something with 3 components. And the first entry is going to be 0 times 5, 2 times minus 1, like this, adding all these up. So I get -2, -2, and 18, 14. Okay, then I get 6 and 3, this will be 9. That one has a 0, I get -2 and -3, -5. And you notice, it's the same thing we got when we were taking the rows and taking the dot product with this to get the entries. And this one, this linear combination of the columns is 2 times 5, 3, 1, -1, 0, plus here, -2, 1, 4, 0, and 6. Oh, not quite. I left off my coefficients, so it would be -1. Okay, here, and then we just add these two, which is 10 plus 2, 12. Then we have 6 minus 1 gives me 5. We have 2 minus 4, -2 and 0, and 0 and -6. And this would have been what we got the first time we did the matrix product, where we did, well, we performed this motion, row dot this, like that. Okay, this is the other way of thinking about matrix times vector. I'd like to do another example of this notion of linear combination. Remember down here, the definition was some vector B is a linear combination of some collection of vectors, provided you can find constants such that B is the sum of the constant times the vectors. Okay, so I just want to do an example like this. So here, this vector 10, 2, -3 is a linear combination of, well, let me give you the two vectors that I want it to use. 0, 2, 0, -1, and 2, 0, 1, 1. And why is this? Okay, why is this? Well, because if we go back to the definition, what I need to do to justify that this is a linear combination of these two, I need to find two numbers, scalars, such that this is equal to, say, x1 times this plus x2 times this. And this one we could actually just look at because of, so let me just start and I will easily find them. This one was made to be, well, I chose these two so that it would be easy to find the x1 and x2. Okay, so I need to write this, as I mentioned, as x1 times this vector plus x2 times this vector, but you notice here, there's zeros here. So whatever I multiply by here is going to be 0 added here. So this would have to be 2 because it's going to be some constant times 0 plus 2 times 2 goes in this component, and this matches here. So this has to be 2, and then the fact that this second component here is 0 means this one has to be 5. Okay, it's not always so easy to find like that, but in this case, it was made to be easy to find these two numbers. And we could just check, for example, if you added, you would get 4. you would get 10, you would get 0 and 2, and then you would get minus 5 plus 2 minus 3. Okay, so this shows that this vector is a linear combination of these two because I can find these two numbers, for example. Well, I'm still working with this one vector, but I've changed things. So first, well, I had two vectors before in our first example, and they had zeros placed strategically so that I could easily figure out that this vector was a linear combination of the two, and I could find the coefficients. And I mentioned, well, they're not all this easy. So now here's like a real one, right? That you have a vector and you have two other vectors of the same length, and you want to know, is it a linear combination? And it's not so obvious. I can't just easily look at it and solve for the coefficients. So how would we do this? Okay, well, how do we know how to work with things like this? Linear system. So let us write what this would mean. So if I have this x1v plus x2w, right? This is the general linear combination of these two. So we want to, well, let me preface this by saying find x1, x2, such that well, this equals b, right? And now let's translate that a little bit further. This is our goal, and maybe we can do it, maybe we can't, okay? Okay, so now x1v plus x2w. Well, this is just the sum, so we take x1 times this vector plus x2 times this vector. This will be a vector, and what is it? Well, it's 4x1 plus 2x2. This is 2x1 minus x2. This is x1 plus x2, and finally minus x1 plus x2. And we want this to be equal to, well, b. So this is 4, 10, 2 minus 3. Look at what I'm looking at. That sounded strange. Look at this. Okay. This is a linear system, right? What's the linear system here? Maybe I'll write it. We know two vectors are equal if this component equals this component equals this component equals this, and similarly, the last component equals this. So this would be that 4x1 plus 2x2 is 4. That 2x1 minus x2 is 10. x1 plus x2 is 2. And finally, minus x1 plus x2 is negative 3. This is a linear system, just like we've been solving, well, 1, 2, I guess technically we didn't solve any today, although we've been talking about them, but the first two videos, we solved linear systems. And this is how I will go about doing this one. Okay, so let me erase some. How do we solve a linear system? Well, what we know so far, we write its corresponding augmented matrix. We perform elementary row operations to transform it into reduced row echelon form. Okay, let's do this. So if I write off the augmented matrix, 4, 2, 1, minus 1, 2, minus 1, 1, 1, and then 4, 10, 2, minus 3. 4, 10, 2, minus 3. And I would like to get this in reduced row echelon form. Well, the first thing I'm going to do, I could divide by the top row by 4. This is not a problem, but it would introduce fractions. It's easier for me if I just swap two rows, and then I can avoid fractions because I want to make this entry here a 1. Okay, so what I'm going to swap, let's see, I'll swap, this already has a 1, so let's swap row 3 and row 1. Okay, and then we will write the corresponding augmented matrix here. So this would be 1, 1, 2, 2 minus 1, 10, 1, no, 4, excuse me, 2, 4, and minus 1, 1, minus 3. And here are our, like this. Now I have a 1 here. So as we know, we want to get zeros underneath so that I can get myself towards reduced row echelon form. I can do 3 moves all in one. I'll take minus 2 row 1, add it to row 2. I'll take minus 4 row 1, add it to row 3, and then row 1, add it to row 4. This will have exactly the effect that I am looking for. This row has not changed. Okay, so minus 2 row 1, add it to row 2. This is a 0, minus 3, and 6. Then I have a 0, minus 4. I'm going to get up, minus 2, and then this minus 4 is minus 8 plus 4, minus 4. Finally, I just add row 1 to this one. I get 0. I get 2, negative 1. Okay, well, here I look in this. I want to make this entry a 1. I don't see any 1s below, so switching rows is not necessarily going to help me. So I can just divide the second row by 3. Or multiply by, divide by negative 3 or multiply by negative 1/3. So I'm going to take minus 1/3 times row 2 times, okay, maybe my arrow doesn't have to be quite so long. And then I get 1, 1, 2. This becomes 0, 1, negative 2, and then I have 0, negative 2, negative 4, and my very last row is 0, 2, minus 1, and now I have one more step. Well, in theory, I have more than one more step, but I know what's going to happen, so that's why I'm saying I have one more step. What's my goal now, though? I want to, here I have a leading 1. I want to get zeros underneath. Okay, so I will multiply 2, row 2, add it to row 3, and minus 2, row, maybe I should put that further down, minus 2, row 2, add it to row 4. And we will write what results. So the first row I have not changed. The second row, I have not changed. The third row, okay, I get a 0, 0. 2 times this would give me negative 4, and negative 4 is negative 8. And now minus 2 times this row, add it. This becomes a positive 4. This is a 0, 0, positive 4. This is 3. Now, okay, you see, oops, well, I think that's good enough. What do we see here? Already we see a problem because this says 0 is negative 8, or if I divided by negative 8, I would get that 0 is 1. This is an inconsistent system, which means that, well, I can still see it here, that this vector, it was 4, 10, 2, and minus 3. This is not a linear combination of, well, the other two, V and W, because I'm running out of space. Or this was our B, right? This was B, we see it here. These were V and W, like this. Okay, so we got no solutions when we put the question of, is this a linear combination of these two, and translated it into a linear system? I'm continuing with this example. I'm going to view it in light of what we're doing today. So first of all, we found out that this is not a linear combination of V and W. Okay, we found that, right? We did a linear system. But the equation, well, what were we looking for? B, we wanted x1V plus x2W, can be written as follows. Well, let's think about what we've been doing today, okay? Let's write these in the columns of a matrix. And then I put this vector, x1, x2, or let's write it with our specific everything. If I put this in a matrix, it's 4, 2, 1, minus 1, 2, minus 1, 1, 1 times x1, x2 equals 4, 10, 2, minus 3. Right? Because this was this column picture here, right? This matrix product is V x1 plus W x2, V x1 plus W x2, and then equals B, okay? Or here, this is all of this times x1, all of this times x2 should equal this. Okay, this is a matrix equation as a matrix equation. I think I have room. Equation. Like this. Okay? So, of course, we found there is no solution here. And not every matrix equation has a solution. Not every linear system has a solution. There is no x1, x2 such that this holds. Okay, we found that. My point is just to view, there's two viewpoints here. Matrix equations is right here, and I want to make this observation. We solved this or found there was no solutions by forming this augmented matrix and doing what we know how to do, which is elementary row operations. And here I'm writing it differently. This is brand new topic of today, matrix times a vector, right? So, this is the same thing is what I'm saying. They're both just this. Whether we look at the linear system or whether we look at the matrix equation. Okay, this matrix equation, maybe I'll write it, then I'll say it generally. This matrix equation is equivalent to the linear system that we wrote. I'll say that we found had no solutions. Okay? Because both of them are just this line, and both of them are addressing, is this vector a linear combination of these two? Well, the answer was no. But let me say something more general. There is an equivalence here. It's one reason we love matrices so much. First of all, we have the linear system with augmented matrix A, B. And then we have the matrix equation written like this, AX equals B. Okay? This was what I solved in that example, tried to solve, couldn't solve it, had no solutions. But I guess in a sense, by answering inconsistent system, that was an answer, not a solution to the linear system though. Okay, these two are the same. So I will write this maybe in the middle, that this and this, I'll write is let me get a better marker. This is equivalent to this. Okay, so this linear system, which we have been solving, we make this augmented matrix, perform elementary row operations. Okay, reduce row echelon form, we read off our answer like this, or we realize it's inconsistent. It is equivalent to this matrix equation where you take this. Now this, if you think about it, this is the coefficient matrix of the linear system. This is the vector that is on the left-hand side of the equals, and this is the vector of variables. It's your unknowns. Okay, important observation, and we will end on this note.